In this video, I'm going to cover the first part of Chapter 8, Casting Steel. Casting is a process that takes molten steel and turns it into a shape that you want. You create this shape by use of something called a mold. All casting processes use some sort of mold, although there are many different kinds. The primary two kinds of molds are permanent and expendable molds. Sand casting is an example of an expendable mold, while die casting is an example of a permanent mold. For the most part, expendable molds have a low initial cost, but a high recurring cost, as they require more labor to produce, whereas permanent molds have an extremely high upfront cost, but a very low recurring cost, as the tooling is very expensive, but after the tooling's made, it's very easy to run many products through it. The focus of this chapter is on casting steel. Let's just take a second and talk about what makes this different from casting cast iron, right? Typically you hear about cast iron. Casting steel is used when you need more strength and more ductility than cast iron can provide. Casting steel is always less desirable from a process standpoint than casting iron for a couple of reasons, but two of the big ones are that cast iron melts at a lower temperature and it flows better when it's melted. If you have a complex mold shape, cast iron is more likely to fill it up and get in all the right nooks and crannies, right? If it's some goofy complex shape, then cast steel is. Cast steel can be designed to fill up a complex, funny shaped mold, but it just takes a lot more thought and planning and engineering time to really get it right. Let's talk about material properties with casting. Cast steel can be heat treated to adjust the grain size. When something has just been cast, it's typically going to have a very coarse grain size, with the coarser grains being toward the inside closest to the mold and the finer grains being toward the outside of the part. Even after heat treatment, these grains will be equiaxed, right? They're all going to be about the same size relative to each other. This is going to result in less strength than something that's been cold worked, in which the grains are stretched in one direction and give you some directional strength. The surface finish of a casting is going to be a result of whatever the mold is made out of. So if it's a sand mold, it just depends on the coarseness of the sand. If it's extremely fine, you'll have a good surface finish. If you have pebbles in there, it's going to be an extremely bad surface finish. If you're doing die casting, in which the mold is made out of metal itself, then it's going to take on whatever the surface finish of the mold is, right? So when they make anything optical grade, the mold is mirror polished, right? There's no scratches. It's like a super finish, 16 microinches. Let's talk about casting defects. These can come from having a pour temperature that is too low. This causes the metal to solidify early. When the metal solidifies, the rest of the molten metal can't get past it, so it's not going to fill up the mold correctly. This is one of the few casting defects that you can see visibly, right? The part will just not be the right shape. Some other defects are voids, which are caused by the same thing, except they're internal, right? So you can't see them, not super good. The other defects that are very common are porosity, which is the result of gas bubbles, which is the result of a excess of certain things in the molten metal, right? There's certain alloys that you can throw in the ladle before you pour that'll reduce the amount of free gas inside of the molten metal, okay, to reduce porosity.